tutorial for just updating on what's going on in our history of inverse scanning series imaging. The actual plan was to just discuss the field data test that's on the agenda. So this will preface the field data, so these sort of two talks, then we'll take a break and move on to other topics after the coffee break. So basically, as we said earlier, the inverse scattering series communicates that it is able to directly and without subsurface information achieve every processing objective that you can imagine. That's quite a tall order. Okay? So, but that's what it communicates. How hard the series has to work in terms of how many terms, what types of terms need to be collected within subseries for different tasks that you might be interested in is a different issue. Okay? It says overall it can achieve. Another issue, what it takes from this series to achieve something. So if you're in the business of multiples, first of all, things are simpler. It's time to time. Traces in, traces out. That's already simpler, and traces in, depth out, which is in depth imaging. If you have a priori information that you assume is reliable, like the free surface multiple removal, that makes the need for terms reduced. If you have no a priori information, no assumption about any of the generators of multiples, anything about the path through which they have propagated, then you have to have more terms. And it's the first term in the free surface removal series is a remover, an eliminator, because of that a priori information. The first term in the activity towards eliminating internal multiples of first order is attenuated in principle, given all of its prerequisites. It's not an eliminator. So that's because there's only no a priori information. It takes a series to eliminate an internal multiple. And so we'll be looking for closed forms of those series, okay? For example. So when you get to depth imaging, just as soon as you go time to depth, things get more difficult. Because you're moving, every time, I don't care what the method is, you move further from the data, things get tougher. If the data's in time, you stay in time, that's easier than time to depth. That's true for every processing objective we have, okay? So right away that brings issues that you have to deal with within the series. Another issue of importance, and you'll see illustrated in all of these cases, is what is actually, if you assume water speed and the velocity gets far and far away from that, the magnitude or the magnitude, what is the distance, the difference between reference velocity, water, and actual velocity matters, and the duration of that difference. If you have a larger, longer layer of a large velocity, the series has to work harder. Work harder means bring more terms in. The last item is how many unknown Earth mechanical properties do you need to assume upon how many velocities, densities do you need to assume are unknown in moving into the series? The more properties that you ask the series to assume are important and unknown and directly deal with an objective with more properties unknown, the harder the series has to work. Okay, so these are issues you'll see played out in tests, okay, here, for when you match, don't match these kinds of issues, okay? And how do we know when they're matched? Okay, we're going to take you quickly through the history. As you saw, Zoe and Wilbert Herrera, they're starting this elimination business in 1D normal incidence, and people could say that reasonably enough, what are you going to do as things become more realistic, multi-D, elastic? But the imaging work started that way too. By the way, the free surface and internal multiple work started that way too. And if you look at Carvalho's thesis and Araujo's thesis, it was all 1D normal instance and grew towards field data. Okay? So here's Simon Shaw's very important contribution. This whole topic here is inverse scattering series depth imaging. Now, depth imaging, direct depth imaging, determine the depth directly without knowing or determining anything about the Earth. You don't know at the end the velocity. You're not. Now, if you have the depth and you have the time, you could back out the velocity. That is something we haven't done. That's something we ought to think about doing, because the velocity is not just an impediment when it's difficult to determine, but it's useful when you can find it. Obviously, high pressure zones and all other issues, aside from imaging, yes? Hazards. So the figure on the right is a model which is 1D acoustic. That's a picture of the velocity as a function of depth. Starts with water. The velocity. The hero of this meeting is Wu. I can't believe it. This is a great hotel. They say we don't. Everyone who we give one of these steals it. So we're not giving you one. We won't steal yours.
It's okay for me.
They brought us one. It was like a huge yardstick. You have to hold like this, like made in 1890. I think a flame came around, pointed at it. So this picture is a picture of the velocity as a function of depth. It's 1D. It's acoustic. The velocity gets larger, gets smaller. And this layer has a speed less than water speed. Just put it. Then the data is generated. This in the center is a water speed image. It's what the first term in G0, V1 G0 says, do an FK Stolt water speed image of the primaries of that data. Okay? And so the water bottom is where it belongs. This is a little shallow, further shallow, and more in error and less in error. This one is less in error than this because it's mitigated by this. In other words, error, and it goes the other way. So the overall error for the, so now what happens is that V1 enters a subseries of the series that is dedicated to do depth imaging, where the original image, the red, is not supposed to change its amplitude. In other words, it's not an inversion. It's not trying, it's whatever the trace's amplitude is at water speed, keep the amplitude, just place it where it belongs. Just to do structure. Clear? There are other terms in the series that do other things. We're just focusing on terms that are dedicated to location and not changing amplitude events. Clear? So then the picture on the right is what happens when the red goes into the inverse series, subseries for imaging. So what happens is the green is located. Okay? The green is a result of 67 terms in the series at that time. 67 terms, V1, V2, V3, sub parts that only deal with imaging. You'll notice that it took less than 67 terms to locate the deepest reflector. Why? Because it had less of an issue. And the series and the data know when to stop giving it things. In other words, it stops. This is like group therapy. This red thing, the difference between normal imaging is each, in normal imaging, every primary is on its own, essentially. You look for its velocity, you put it where it belongs. Okay? Everything that the inverse scattering series does, for any goal, free surface, internal, imaging, is all cooperation of data with data. The data interacts with itself. Multiplicatively interaction. So times and amplitudes come in. That's why you get that V1, 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 V2. That was a data thing multiplying. If you look at the SRME, data times data. If you don't allow me to have data times data, then you need to give me subsurface information. Migration, ordinary migration is linear. So whatever happens to the event, it doesn't talk to another primary. Okay? You might use different primaries, for different offset for a given reflector, yes, for common image gathered flat, but this primary and this don't communicate. That takes trace times trace, just like the multiple removal activity. So let's just play that again. So what happens is, that instead of having individual therapy, the inverse series says it's group therapy time. The data's got to get more involved. The earth is too complicated. Let it, just give it the task. You figure out what you want it to do and search in the series for the sub-series that has one issue on its mind. It's called isolated task, sub-series, okay? So that sub-series, terms of it were located by Simon. Let's just play it again. By the way, when this was first seen by Simon, we thought the series blew up. His screen went green. We were ready to talk to the sponsors, this is over. And then he just persisted. He was just upset for a while. You know, he was in group therapy, none of them were happy about it. And you understand? And they settled down. And when they settled down, in other words, this one got well adjusted, ready to live with society before this. And if you looked at it in the offset domain, which you'll see in a minute, its common image gathers flat. And it doesn't get any more help. That's interesting, right? It decides, and you'll see in some analytic activity, how it makes that decision. It's interesting. Where is that intelligence coming from? The directness. In other words, this is not a search. This is term after term, each term doing something. And the word direct inverse and purposeful are together. Every term there is not looking, it's doing. Doing something specific that only it can do. And certain terms determine whether they need to do anything. That's very amazing to me. So Bob said yesterday, I said, I know you, I told Bob, I said, I attribute human qualities to the inverse series. And Bob said, it's intelligent, but not human. So I said, my wife said the opposite. I'm human, but not intelligent. Between me and the series, we've got a partnership. Okay, so that's 1D. Not only is it 1D normal incidence, the contrasts are small. If you look at the velocity, there's small changes. If you gave Simon Shaw's algorithm large contrast, it would not give you the depth. It didn't have enough capture. It had enough capture for that degree of difference between the velocities. Either if you made the contrast bigger or the layers bigger, his algorithm would fail. Clear? How would you know it would fail? Common image gather wouldn't be flat. You'll see that in the next. Here's the pre-stack version of the same model. And the group therapy starts. Common image gathered flat. You notice the one on the bottom got flat first. And there's no alteration. There's no NMO stretch here. Okay? You'll see later an AVO example when we get to the elastic world where a zero crossing is preserved at depth. In other words, none of this CIG flattening and then ironing, and losing that zero crossing. So this is very early, and again, 24 terms, or in the other case, 67 terms. Along comes Bob Keyes, who was at ExxonMobil at that time, and finds a closed form for infinite number of terms. That changed everything for us. Because term after term, you can have round-off error. Each term you compute, right? Then we were worried. I remember having conversations. So suddenly there was a closed form for a certain type of capture, yes? An infinite number of terms of a certain type of capture. 1D and not all extent and all magnitude of the error and duration of the error, but within a certain degree, it was a closed form. Why that changed the world for us is we didn't know whether we were going to put a variable background in or not. And Professor Fang Lu, who was a graduate student at that time, in his thesis, we hedged bets. Because people would say, you know, you have this, why don't you put some smooth background in? Yes, get yourself some help. So we didn't know, and we still don't know for further capture what we'll do. We always stay open. But once you had a closed form with a homogeneous background, why? Because the homogeneous background, those G0s are analytic. So you can see the math forms and you can find a closed form. Once you start doing variable background, what are you going to do? WKBJ, it's high frequency. There's no such similar exactness that you can depend on for analytic forms. So that at that juncture, we said no variable background yet. And all subsequent work of Fang and Zicheng and others who worked on it were all constant background, closed form for more capture. 2D, okay? And so here you have a salt. This came from Fang Lu when he was a graduate student, and he was at ExxonMobil working with Peter Training, this model. Okay? So those are big contrasts, 4,600. The reference is 1,500 meters. Those are big contrasts, a lateral variation. Some series with more ability to capture contrast and duration than Simon had, and also was 2D and acoustic, produced the following. You follow the way I'm talking? Capture for different duration and size of difference between water and velocity. So here's a water speed, FK slope migration. Should we shut the lights? Is that going to help? No, it isn't. This is not the water speed. What happened to the water speed? The water speed image is missing. Okay, this is, in other words, the first step is a water speed image. The water speed image, probably good with Bob Stoltz saying we don't show it. It's a water speed image. The only thing that imaged in the water speed image was a water bottle. This, in other words, the red are the targets. This is Fang Lu's algorithm, which is a capture of terms, not all terms, that deal with lateral variation, that deal with, so what do you see here? You see if we don't have the example with the FK migration, that's stunning. Because the degree of difference between the first step, which is the water speed, and this is dramatic. The important message is, what does this cost? The cost of this algorithm is 30% more than a single water speed FK migration. I'll repeat that. The most costly part of this algorithm was the picture I'm not showing you, unfortunately. It's not in this slide set. Professor Fang, do you have that water speed image somewhere? Maybe after we can show it, because it's such a dramatic difference. So, you can show it, oh, thank you. This is her 6th contribution for a PhD. You should be a chair professor when you leave it. Okay, so this is the water speed image on the left. It's a different scale, but it's the same model. In other words, the images, the actual are red, 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 red. Top salt, base salt, yes? So the only thing that's on is water body, because conventional puts what's water speed. And then Professor Fang-Lu's result is this, with partial capture of terms in the inverse series that leads to a closed form, where this result is the most costly part of the algorithm. And we all know how rapid and fast that is. Yes. So that's a very positive, because here, this guy here is this image. And certainly there are things wrong with the walls here, and there are diffractions that haven't come out. But it's a big step forward for 30% more cost than a single water speed migration. So then, is Z, we have to go back for Z jump? Sorry. I thought you should see that instead. Okay. Thank you. So then, this has some degree of capture. Then a student, Zicheng Wang, who now is at PGS, yes, graduated last year. This is further capture. In other words, this is higher order imaging series. The LE means there are terms in the series that are exclusively become alive when you have lateral variation. LE means lateral exclusive terms. What do I mean by that? The terms in the series which have a partial respect to X or partial respect to Y. If you have only 1D medium, they're gone. They're not there because there's no lateral variation. If you have a lateral varying medium, they kick. So there's some terms, lateral, just the cost of this, you see the improvement in terms of the walls, again, essentially for free. So this was very encouraging. Here's the fault shadow zone, water speed. Oh, yes, that's water speed. Okay, no problem. Water speed, you got to water, everything is off, you understand? And you'll see, this is Professor Fang-Lu's result, and then you see Zicheng. Zicheng's result is not full capture. It's again partial capture. We don't have full capture. Well, we had enough. If I would have taken this result to field data for free, right? So you just look, and then you look for whatever you're going to do after, for a single FK migration. The problem is, as I alluded to yesterday, I went to BHP Bulletin one day, and Mike Richardson mentioned, by the way, I'm sure you are aware that most reflections are density. I said, oh, of course I'm aware. He said he couldn't believe that anyone would not know that. There are cases where it's mainly velocity, but many other cases where density drives reflections. And so with that, and then to Imtiaz's, we understood that we had to, how should I say this? This whole method was assuming, as I said yesterday, that in traditional current migration, all you need is velocity to get depth. So this assumed that the only thing we need to tell the inverse series that we don't know is velocity. Okay. And so that's a mistake. That's why right now we don't have depth imaging under the salt without the velocity. That is the point. And dealing with that issue is what we've been about. Okay? So we had to go to multi-parameter. First, two-parameter velocity density, yes? then elastic. You'll see all that evolution. Understood? Okay. So this is the work of Halyan Thang, sitting behind Clement. Okay? Multi-parameter, first acoustic, then elastic. Doing the inverse series where 3, in the elastic case, parameters are unknown. VP, VS, and density. Okay? And doing the tasks. For the multiples, we didn't need to care about it. We already knew they're model type independent. They don't care what model. But the imaging, we didn't have a model type independent. So we're going through more and more complete models. So this is the linear term. Data is G0. This is acoustic. In this acoustic world, there are 2 parameters characterized here as bulk modulus and density. What alpha 1 is the linear approximation to the relative change in bulk modulus, and beta 1 is the linear approximation to changes in density. And so this is the first, G0, V1, G0. V1 is a linear combination of linear approximation, first order in the data. Then there's a relationship that between the second equation, you see G0, V2, G0 equals, in other words, the form to invert this for alpha 1 and beta 1 is exactly the form to invert this for alpha 2, beta 2. G0, V1, G0, G0, V2, G0. The inverse step is always the same. Remember that yesterday? It's the right-hand side, there's a lot of multiplies. It turns out the multiplies on the right-hand side are divided. There are terms that have integrals, and there are terms that do not have integrals. The terms that do not have integrals are dealing with amplitude issues, like AVO, transmission issues, issues that occur locally. The integral here, whenever there's an integral, it represents that the problem that the series is dealing with has duration on its mind. So the fix has to have an integral, a duration, some form of integrating over. Depth imaging is, the issue there is not just the wrong velocity, is how long has it been the wrong velocity. There's a duration issue to the fix. So it turns out, and we don't have time to go into, we can show you, for example, an example where you have one reflector, yes, one reflector, the only reflector. You take the inverse series through this, and you give the inverse series C0. It's the only velocity for imaging. And these terms are 0. They're 0 in 1 parameter, they're 0 in 2 parameter. These are terms which come alive when there's an imaging issue. And so watch how they determine that there's an issue, yes? So what was this set up for? This was set up to deal with the issue that we were discussing yesterday. Let's say you have density change, and the velocity doesn't. You can have sediments like that. You don't want those reflections in the conversation. If you assume a velocity-only model, then every reflection is in the conversation, dealing with imaging issues. So as soon as you set up this world of 2 parameter, what amazes me about this is it knows it has that issue. So it, without us, in other words, this math we didn't make up. This is the second term in the inverse series. We're looking at what it's doing. These terms will show you in the next slide. If you have a density change across a reflector, a density change, but no velocity, it's not an imaging issue. Understood? Because the velocity is the same. Velocity, it doesn't have to correct. So that kind of reflection we don't want in that red line talking to each other for imaging. Okay? So this automatically excludes that type of reflection. Let's show how. You understand what I'm saying? That integral deals with only reflections that have a velocity change. If they're not in this conversation. Let's consider what happens at a reflection where this is an exact expression, it's like Zopert's, but acoustic. This is the exact expression for the reflection coefficient as a function of angle, one interface. You have above, you have C0, rho 0, below C1, rho 1 as a function of angle. This is R of theta. You can find that in the book. Okay? The interesting point for us is the point to know. Let's say you're across a reflector where the velocity didn't change. So C0 is C0, C1. In other words, we're worried about a density changing, only density changing reflection, yes? If you have only density changing, then C0 is C1. Then this factor, 1 minus sine squared, factors out. This is 1 minus sine squared, and they cancel. Then you get the reflection coefficient is independent of angle. If you have a density change and not velocity, R is independent of angle. If you look at the first equation, this first equation, alpha 1, beta 1, it's just a kind of acoustic AVO thing. If you give me two angles, I can solve for alpha 1 and beta 1, and I can solve for then alpha 1 minus beta 1, yes? Two angles, you get alpha 1 and beta 1. When you do that, you get the following. Alpha 1 minus beta 1 is R of theta 1 minus R of theta 2 over this. So, if you're at a reflection where the density changes but not the velocity, R is independent of theta. Clear? R is independent of theta. The numerator here is 0. The numerator is 0. The integrand is 0. So, if the density is the only thing that varies, there is no, that reflector doesn't come into the conversation between primaries. Clear? That's already impressive. Not impressive of us at all, impressive of the inverse series. That it somehow is, its machine anticipates that issue and precludes it. We didn't build this, you understand? We didn't, let me do something that gets density out. We just wrote the second term in the inverse series, where it allows for density and velocity both to vary. Okay? It starts to deal with that issue. Okay? If you make the inverse series where velocity is the only thing that varies, it can't separate. Every primary is in. Okay, so that was useful to see. This generalizes to the elastic case. Again, Halyan Thang work, the elastic equations, 3 parameters, A rho, A gamma, A mu up there, 3. And there's a term, a moving term in the elastic world with integrals, and there are terms that don't, and the term A gamma 1 minus A rho 1, they will be 0. Those terms will be 0 if both the VP and the VS do not change. Both. Let me explain. When you do imaging in the elastic world, there's a reflector here that it's needing to locate. It doesn't know beforehand or make an assumption about what kind of image you want. It could be PS. It just says, you want to locate this? There are PP, PS, different primaries that can contribute to that image. So it has to allow this for velocity and then velocity of both a P and S variety to be needed to be assumed to be unknown. That's one of the things that's why we're talking about P-only modeling. We don't want that complexity. We're willing to just live with, get down there with P, get back with P. The inverse series is saying, I'm going to deal with imaging where any possibility to that image in terms of P and S is, so it's too much work for us, too much in needing terms. So anyway, that's, so this is the kind of image we're looking at. These things on the outside add up to something like the data. In other words, it's producing a something like a reflection coefficient. What this is, it's doing migration inversion. It's saying first migrate down there, and for us, first migrate down there, and here we'll stop because we're not trying to invert. It's this thing that is the sum of these things is just like the DPP. Yeah. Okay, let's show some tests. Okay, this is a constant velocity example, but the density changed. Yes, the density changed. So the water speed or the image, in other words, it's water speed, water speed, water speed. Clear? The density changed. You put it in that acoustic two-parameter inverse series imaging, and this is the water speed image, and this is the inverse scattering series imaging. It's the same, because those integrands are zero. Okay? So it doesn't mess things up if there's nothing to do. Okay. This is constant density of velocity varying. So you have an imaging issue, and it fixes it. In other words, then those integrands will not be zero. Yeah? And it's got some work to do. Both changing, no problem. Okay? And then velocity and density both changing. Elastic, polarity reversals, to give you some. Here's an example. This was given to us by ConocoPhillips, Doug Forster, and Bob Keyes, AVO people, to give us a zero crossing. They said, don't worry about, this was in the time of Halyan, you know, looking for changes in VP, VS, and rho directly. They said, we'd be happy if you could just bring that zero crossing image to its depth and don't lose the zero crossing, so that we know it's a zero crossing. Because in the attempt to get it the right depth, you do this common image gather, you know, tomography, and yes, and you can lose the zero crossing in that filter. So that's what this is about. Here's a zero crossing. This is, I believe, Shu Li's work, yes? Came after Halyan. So it's a zero crossing at 28.45 degrees. Let's see, what was the model again? Okay, you don't have an imaging problem. But the velocities, it's elastic, the densities are changing, but not the velocities. So the original image and the inverse scattering image are the same. Now that the velocities vary, yes? So you have an imaging issue. And then the ISS image is flat, and not only at the right depth, but the zero crossing is preserved. There's some kind of numerical thing running around there, one of those traces. Okay, So basically, the idea is the inverse scattering series says the following. If you say, here's an event, and you say, is that a primary or a multiple? I don't know what to say. If you give me the model that generated this data and that event, we can probably figure out what it is, yes? By timing and things like that. If you give me all the events in the data, then it doesn't need the model, because the events will talk to each other. That's what SRME is doing. What we're saying is, if you know it's a primary, you say, this is a primary, let's find the depth. I have to have the velocity. If you give me all the primaries, they do a conversation that the inverse series sets up, and that conversation can produce the depth of each one. And how do you know when they're done? When it's a common image gather flat, it's done. Remember when that movie stopped jittering? It stopped on its own. There were some places kept agitating, they needed more terms. Others that were deeper stopped because they were done. And no more contributions came to them. So so the idea is to extend just as top and base solve to combine to remove internal multiples within solve. These two primaries can be used to depth image the base solve. So it's in some way the opposite of our current way of not just in terms of letting data talk, but we tend to not want the reflections on the image. We smooth top base solve after we work hard to get the velocity, yes? In this procedure, you want the sharp changes because they are the reflections that are going to be the communicators. It's as if you smooth and lost sub-events and then said, I want to take primaries out. You want the sub-events. So now imaging is seen as, in the inverse scattering series, as a collective activity, just like multiple removal. Okay. Kristin, at some point we said, let's try some field data. Yes? And we did. And this is data in Norwegian Sea. It's data that Schlumberger processed, a whole group of companies owned, Exxon, Statoil, and several others. Okay? Own the data. So in publishing this, we have permission legally and technically from all the companies who own the data and process the data. Okay? So there are criteria for ISS imaging to be effective. So the point is that what we just said was not the plan. This was going to be the plan. We're just going to remind people of what we told them last year so they get a sense of the status of things and what we've done. But there are criteria. There are things that have to be satisfied for inverse scattering imaging to be effective in directly predicting the depth without a velocity model. You have to have adequate capture, inclusive of terms, for the difference between actual and reference properties and the duration of that difference. It turns out, with the way that this has been formulated from the beginning and till today, unfortunately, has a low frequency sensitivity. That should have been avoided. I take responsibility for that. In going forward, part of the plan is that's not going to be there. Let me explain. When you see these images, it was all in terms of boxes. We made a mistake that no migration person would make. Migration, its strength is it stays in data space. It doesn't output in model space. It might need the velocity in model space, but it never makes the method go to model space. This was looking at the world in terms of boxes and the interface of boxes, mislocated, and move them. To move a box is a much more demanding operation on low frequency than to move a spike. Here's water bottom, here's sub-water bottom, wrong location. To make it right location, with this picture, you have to build that. You have to build this. That likes low frequency. If you did this the way every migration person would have done, and how we should have, and how we will go forward, is look at this as spike, an image. This guy is some image mislocated, and we need this mislocated one to be where the image is. In other words, your migrations don't look like boxes, they look like data. Data moves. Okay? This is like data. This is boxes. You should never gone in that world. Okay? That's okay. What's the difference? As you can tell, if I have to make a box, I need to have enough low frequency to get the jump. That's the whole WI business, right? To get that. And we're fortunate that we have Professor Feng Lu, who found a way for this algorithm to regularize it, to make that happen. Okay? That by itself is a huge contribution, which probably people should look at for other applications, because it's clearly effective, and including on field data. Yes. But let's explain. So this way we all understand this guy, because the thing we call alpha 1 and alpha 2. Alpha 1 is a box. It's a linear estimate to alpha. Alpha is the difference between actual velocity and reference velocity. It's box-like. Yes. If we had done the intelligent thing, which is don't look at the inverse series for boxes moving, but spikes. So you're a spike, you're a spike, you're a spike. Here, the inverse after linear has to build this box. Clear? To get this to the right depth. If it spikes, the inverse has to remove this spike. It has to build one like this, the negative, and make this one. Add this to the original, it kills this and makes this. The terms beyond linear have to do this. This has no zero frequency. You don't need zero frequency, two opposite spikes. There is no worry about low frequency because this doesn't need it. This definitely needs it. Okay? So that was a strategic mistake on my part. Okay? That has led to consequence. But due to resourcefulness of some outstanding people here, that was mitigated. That's what this is talking about. Okay? Data regularization for that box moving. Yes? And then a model type match between the inverse scattering series imaging algorithm and the Earth that generated the data. That's what Halyan was talking about. Let's say the Earth, a realistic model for the Earth is elastic. And I assume 2-parameter acoustic. But a good match for the data there is elastic. You will see what happens when any one of these things are not satisfied right now. And then what happens when they are satisfied. If all of these are satisfied, the inverse scattering series gives you the depth directly. Okay? In other words, these are the criteria based on all our studies. So what we're going to do is take you through an example where each one of them is violated and satisfied, and you'll see the consequence. Yes? In isolation. Just make it adequate, inadequate, in terms of the strength of the algorithm for the contrast and duration issue. Okay? Then this guy's data regularization will do it without data regularization, and we'll do it with data regularization. And without data regularization, it doesn't move. The water speed image is the image. Okay? So with the regularization, it moves to the right place. So these are each essential. And this model type match between, this is the real tough one. Because these two, common image gather flatness will tell you you're there in the output. This, the algorithm, it will, in other words, including in the field data, you give it an algorithm which was acoustic in this case. We assumed that the near water bottom was not rock, that it was mud or something, somewhat acoustic. Yes, we were hoping for that kind of thing. And then we get a common image gather flat, where it wasn't flat with water. Then it becomes flat, yes? Let's say you had the wrong model type. If you had the wrong model type, then that flat is not the depth. If it's the right model type, then that is the depth, because these two criteria have been met. Okay? So in the water bottom, I'm just trying to explain how we go at this, yes? Okay. So what we're going to do is show you very simple examples of with and without each of those criteria, including map this, and then show you the Kristin data. What convinced us that the critical parts of this were viable. It meant that this and this were held. And if we had the right model type, that was the depth. If it wasn't, if that was the model type, it would have been the depth. Clear? We have no measure on this, a way to know. Common image gather will tell you if these two are met. Okay? Synthetic tests examining each of these above criteria. Adequate capture inclusive. So here's some model. Here's essentially a Simon Shore. It didn't have enough capture for this contrast and duration. It's not flat. This found loose capture, adequate capture. Yes? Algorithm with more terms than this. Okay? Next, data regularization. Here's an example of water speed migration. Here's low frequency in the data, so you don't have an issue. ISS with diminished low frequency. It doesn't move. Gave you the same as the water speed image. It can't build a box. We understand? With Fang's regularization, it does like having low frequency. That's a crucial thing that I would encourage people to look at. For other purposes, perhaps, yes? As with many things that Fang does with jewels. Okay, model type match mismatch. This is to your question yesterday. Yes? So this is variable velocity, variable density. This model. Okay? So the model is a two-parameter acoustic. Model with variable velocity, variable density, water speed migration. This is the imaging, let's say Fang's imaging, where the inverse assumes only velocity varying. See how mixed up it gets. Okay. It's assuming all the reflections are due to velocity. If you let it, so this is constant density. That's not a surprise, you saw that picture already. And here is variable velocity. Okay, there, not a problem. In other words, constant density, variable velocity, and now both change, not a problem. As long, in other words, here, the velocity and density varied. The algorithm, the imaging, assumed they both are varying. They both are unknown and being dealt with. What you saw in the first example is if both were varying, but you assume one was varying, it didn't work. So that's where the match had to come. But please understand, this is flat. Flat, why? Because if that data had come from a velocity-only world, the algorithm had enough terms to make it image in that world. And it was also regularized. So it had those criteria that arrange for flatness. But if you don't have model type match, it's going to be the right depth in the wrong Earth model. Okay? Get the point? We have no criteria for the match. That's why we're keen on. So first of all, we'd say we better make it elastic isotropic, minimally realistic. That's what our AVO people have taught us. No one does AVO with acoustic. I don't want to say another sentence, I'll behave myself. Okay, so that's basically the lessons that we took into, and then the last, this you've seen already, the polarity reversal preservation in depth. Now here's the field data. And authors of this, Ed Craw, from Schlumberger, Lasse Amundsen from Statoil, a whole group worked on this. Yes, and a whole group within M-OSRP, and I apologize for not putting all the names. This was the wavelet, we needed the wavelet. We all know that from all of these things. And this Halyan Thang's work on getting the wavelet. So this was very shallow. We just wanted to see if in the shallowest, simplest field data you can imagine, whether the things we looked at have any chance of showing viability, the possibility of happening, yes? So this is the water bottom, it turned out, is a density change. How we knew that, we're all, this is a plot of alpha 1 minus beta 1. That thing which is a, yes? Alpha 1 minus beta 1 tells you if a velocity change, if it's acoustic. Remember, alpha 1 minus beta 1 is 0 if only density changes. The water bottom here had a 0 there. So it said it was a density change. So the water and the sub-water bottom first had the same velocity. Clear? That's why the water bottom, this is a water speed image. The water bottom and the sub-water bottom both became flat with water speed migration because the change, there was no change of velocity at the water bottom. Water speed, water speed. The third guy is an internal multiple between the water bottom and the first reflector. It has the same speed. So it's flat. This one had to move out. This one we looked and went into Professor Fang Lu's velocity only, right? Velocity only, HOIS, and it produced flat. Yes, it flat and moved. For us that said issues of regularization and model type adequacy. It is very simple. I understand it's simple, but it's field data. It was our first toe in the water on field data, said that for the model that he's assuming, which is velocity only, they found the depth. If everything is velocity only changing here, that is the depth. If velocity and density are changing along the road, yes, then it isn't. For us, what did that say? It meant critical, in other words, if we couldn't deal with bandwidth, then that wouldn't be flat and move. End of story. You saw an example. When the low frequency was missing, the HOIS image was this image. The series just... So it meant that viable for me means critical practical factors are at this moment not an impediment. Okay? The ability, are we ready for salt? No. Okay? But it means this is not something that it should be shut. Okay? If with the data regularization and the HOIS this didn't go flat, we probably would shut it. It means those kinds of things you haven't been able to deal with, and it's not a matter of more terms. For example, if you don't do regularization, I could put the whole inverse scattering imaging series in there if I ever knew it, and it wouldn't work if it's not regularized. Clear? So those are why we said we call this a very low ambition but clear indicator that that is possible. Now go make it capable. Make it in your, make it a contributor. Does this make this in the toolbox of imaging? Very far from that. Okay. So I wanted to be clear what the story is. We then came up with a strategy to deal with this issue. 3 points. One is there are three parts of that strategy. And you'll see the first part discussed in the next talk, which unfortunately I'm giving, okay? Right now, I mean in a minute, is keep it elastic, but don't ask it to deal with every possible path that brought you to the reflector. Just make a compromise to make this reach subsalt in our lifetime by assuming that the paths you're interested in are only P. Okay? That's going to be a part of this. It's going to be elastic, but only P. That's number one. Number two, make spikes move. There are issues in that box that are more than just that bandwidth in multi-parameter. Why? This is a space filling function. This guy, space filling. This is local. There are implications for this space filling thing in multi-parameter that are not just bandwidth. We don't want this space filling business. For those who, okay. In other words, you have these images, it's not just this and this. All the space above it is talking. This is alpha 1 talking to alpha 1. We want these guys to talk to each other. Get it? Local things talking, not space-filling things talking. Okay, so item 1 is reduce your ambition of elastic imaging, direct imaging. It's going to be elastic, but only allowing the possibility of p-paths back and forth. That's going to reduce the need for 3 parameters. Get VP and rho. Okay? That's 1. The other is spikes. The third is model type independent depth imaging for structure. So those are a plan. Those are high ambition goals, fundamental goals, and they will progress while others pay the rent, like the multiples and other things. Yes, elimination and spurs. So that's basically where we are. Okay, I guess this is a cartoon of what happened then. This viability. Not viability, we need a viability for spell check. Field data. That FILED is an approximation to field data. If someone said, Weglein never said it's going to work on field data. He said it was going to file data. So is it time for a joke? It's time for a joke. And Garrison can bring this joke back to Petrobras. After Lira from Petrobras got his PhD with us and went back to Petrobras, the management said, okay, your Weglein signed a PhD. Yes, okay, you're safe. Okay, you're safe. You actually need the velocity to get the depth, right? He said, no, you don't. He said, come on. He can't hurt you anymore. You're back home. We're deprogramming you. Okay? So he realized he needed to be with his, Romanelli and Carlos Cunafilo, all the people who do depth imaging then. So they went out for beer. They were trying to regularize him to remember he's back and safe and all. So he said, well, okay, I'll tell you the truth. When Weglein needs the depth right here, in this location, of course he needs the velocity. He's crazy. No velocity. Didn't you ever hear velocity is distance over time? When you lost that formula? What he means you don't need the velocity, he means if you want the depth here, you don't need the velocity in another continent, or another planet. Oh, okay, welcome home. So that's a true story, by the way. You need to have some humor about the whole thing. So I appreciate, and we appreciate, the opportunity that you give us to do this kind of work. You know, it's rarer and rarer to be given that length of time and that support. And it will work, and it's going to take time. I mean, work in the sense of enter the toolbox work.